Hey guys, hope you're doing well. What we're going to be covering today is we are going to be covering why we have seasons. So you should be in your note packet for this. I'm not sure what page it's on. Probably, if I was guessing, maybe the fifth page or something like that. I'm not sure off the top of my head, but it should be right where we left off last time we went over notes. So it shouldn't be too hard to find. But what our learning target today is to be able to explain how the Earth's rotation and revolution about the sun affects its shape and it's related to seasons. Okay, so really going to look at seasons for today and kind of the shape of the Earth as well. Okay, so our first thing we're going to look at right here is some review, some things we need to make sure we understand. So the first thing we need to know is that we define a day on Earth by our rotation. All right, 360 spin on our axis. We define that as a day, and that takes us roughly about 24 hours. It's actually a little less, but we go about 24 hours. And so we also define daytime as us facing the sun and nighttime facing away from the sun, depending on our position on Earth. And also, we know that it takes about 365 days for us to go around the sun. If we're going to be more accurate, it's 365.25 days. It takes us that time for us to do a revolution around the sun, so it's between rotation and revolution. And so we know every 4 years we make up that extra 0.25. We've got those 4 years and a leap year. Okay, so we define that as a year. So why do we have seasons? So we've already alluded to this a little bit, but the reason we have seasons is because of our tilt on our axis. Okay, we are tilted at 23.5 degrees, and that's the reason we have seasons. So let's look at why we, or some reasons, or what are the things that do not cause seasons. So the first thing is we don't travel in a perfect circle. Okay, we know from Kepler's first law that we travel in an ellipse. It's like an oval. And so with us traveling an ellipse, there are times where we are at perihelion and aphelion. So perihelion is when we are the closest. So if you look at this image right here, if we're looking at it in miles, we're the closest right here. And then we are the furthest away at aphelion, and we're looking at an ellipse. And so a lot of people will say that the reason we have seasons is because we get closer and further away from the sun, which is not accurate at all. Okay, we do get closer and we do get further away from the sun. But if we're going to say we get closer to the sun in summer, that's not true. If you look right here in July, we're actually the furthest away in our orbit around this, our star, which we call the sun. And then perihelion, which means we are the closest to our star. That's actually January, so for us that's winter. So it's not really accurate. We can't really say that we get closer and further away from the sun and that is the reason we have seasons. It's not. It's not at all. So we can't really make that argument. Some people do. So the reason we have seasons is because of our axis tilt. We are tilted at something that you guys have to memorize, 23.5 degrees. And that is the reason we have changes in seasons. We stay at that 23.5 degrees tilt. We know there's something called nutation, which we know that wobbles, which we talked about last time we were together. But we stay average about 23.5 degrees. And so depending on that tilt at 23.5 degrees, in relation to the sun, will dictate what season we experience. Now, it's opposite depending on what hemisphere you are in, but depending on, we'll probably cover most things in relation to the northern hemisphere just because we live in the northern hemisphere. But just always know it's always opposite from our seasons for theirs in the southern hemisphere. Okay, so just kind of so right here is a good image to look at. Okay. One thing you guys need to get good at is knowing and looking at images like you see on the right and knowing if I give you a question saying what season is the northern hemisphere experiencing, you should be able to do it. And here's a way. So right here we see that the Earth is tilted at a 23.5 degree axis tilt. So let's see if I can get a color here. So right here this is about a 23.5 degree axis tilt. So if you look right here, the sun's rays are hitting us this way. So one of the reasons that it's warmer at the equator is because of the angle at which those rays hit us. So at the equator, you can see these rays hit us at a 90-degree angle. And so based off that 90-degree angle, it should be the warmest at the equator. Okay, should be the warmest at the equator for us. All right. So the way those rays hit us at the northern southern are more drawn out, so that means it's not as warm. But if you look right here, it says that it's winter for us in the northern hemisphere. If you notice, in the northern hemisphere, we're tilted away from the sun. So that means it's going to be colder for us. So actually the opposite in winter for us in the northern hemisphere would be summer. And if you notice, the southern hemisphere is tilted more towards the sun than we are here. So that's why it's the case. Now after winter, we experience spring. If you look at spring and fall, so these two images right here, you'll notice they're really, the angle is the same. You notice that we're still tilted 23.5 degrees and somewhere in this direction over here if I'm doing it to my cursor. But if you notice, they're the same position. They're still pointing over here, and it doesn't appear as if the northern or southern hemisphere is pointing more towards or away from the sun. It's actually not. It's actually pointing towards somewhere over here. So during the spring and fall, to be quite honest, they look the same. It's just right here, the Earth is on this side, and then in this image, the Earth is on this side in this image. But if you notice, it's not tilted towards or away from the sun in this position. All right, so we have an equal heating of the northern and southern hemisphere when we have spring and fall. Okay, that's why we call them the equinoxes, the vernal autumnal equinoxes, because we're getting equal heating at the equator during those times. Now, if we go over here to the summer, all right, during the summer, what you should notice is if it's summer in the northern hemisphere, we should be tilted towards the sun, and we are. All right, if you look right here, we are tilted towards the sun, and so it is summer for us, northern hemisphere, because we are tilted towards the sun. And the way those rays hit us is more of a direct angle as opposed to the southern, because if you look at the southern, it is winter for them, and you notice they're tilted away from the sun, so they're not getting as much sunlight. Okay, excuse me. So right here is another image, same image we looked at, but it's just showing you the light in which it hits the northern and southern hemisphere depending on where we're at. Right here, if you notice, sun is right here. We're still tilted somewhere over here to the right. So if you notice, this is either right here it says autumn and this one says spring. We're not tilted towards or away from the sun here. So this is between the seasons, between the extreme seasons like summer and winter. Now if you look right here in the northern hemisphere, okay, we are tilted away from the sun. All right, so it should be winter for us. And down here it should be summer in the southern. If you notice, there's more sunlight hitting the southern hemisphere if the red line's the equator. This right here, we're tilted on this side to the sun, so we're experiencing summer, and in the southern hemisphere, we're experiencing winter. So why do we have seasons? One is because of the tilt, but it's the reason that we are tilted, we're not sure, but the way the rays from the sun hit us is the reason we have seasons. So if you look at this image right here, I'll go back here if there's some notes you need to get down. What we do is we call the incoming radiation that's coming from the sun, we call it insolation. So insolation basically stands for incoming solar radiation that's coming in. And the way that those angles hit us during our seasons dictate, or during where our orbit around the sun dictates the season we're experiencing. So right here is a great image. Right here, the sun's over here, hence the rays are coming in. We are tilted towards the sun. Okay, and if you notice, if this red line is the equator, more of the northern hemisphere is lighted than the southern. And if you notice right here, if the sun was right here, the way those rays are hitting right here is at a 90-degree angle. So you have more concentration of insolation hitting that area than you would have in the southern hemisphere. So right here it gives you some like yellow lines showing you how those rays are concentrated. So the reason that we have seasons is because the way those angles of the sunlight, that insolation hits us. That's really the only reason why we have seasons. We're tilted, and depending on that tilt and orientation around the sun dictates what season we have. Another reason that we're tilted on our axis and we have things that change throughout the year is due to that tilt. We also experience different amounts of sunlight during those times. You can see here in the southern hemisphere, if we're tilted towards the sun, this would be winter. And if you notice, not much of the southern hemisphere is lit up. That's why during the winter for them down there, just like it is for us, the days aren't as long. You don't have as much direct sunlight as you would in the summer. Right here, if you get closer to the South Pole, there's some days, or some times throughout the year when in the winter for them that they experience a full nighttime for them. So they experience some different times. Okay. So right here, another little kind of reminder: summer, we're tilted more towards sun. Winter, we're tilted away from the sun. Okay, so the review right here is the Earth's seasons, and they're not caused by the differences in the distance from the sun throughout the year. It's because of the tilt. Okay, it's not because we get closer or further away. So this is a great image. I encourage you to pause this, look at this image, study it, and know it. Okay. The last thing is the Earth's bulge. Okay, this is something you guys have to know. So right here, the bulge, when we look at Earth, a lot of people, if you get on a globe, it looks like a perfect sphere, perfect ball. One thing I'll go and tell you, it's not. When we look at Earth and we look at its geometric shape, it's not really a perfect circle or a perfect sphere. It's actually an oblate spheroid. So what that means is it's kind of like it's like a perfect sphere, but it's like someone took both ends and kind of scrunched it in, so it's kind of fatter around the middle. All right, it's been kind of squashed. It doesn't really have a perfect diameter all the way across. If you were to go north, south, east, west, it's not a perfect diameter. Okay, so when we look at it, the reason that this is the case is because of the rotation of the Earth. Due to centrifugal forces, the Earth kind of has been spread out throughout time, and so what we have right here, so if we're looking at diameter, is that we're actually wider than we are tall. So we're not quite a perfect sphere. So really what I want you to take away from this is that we're not a perfect sphere. Okay? The Earth has a little bit of bulge. The Earth is not perfect. It's not a perfect sphere, but it's almost kind of like if you were to take a ball of clay or ball of Play-Doh and think it was a perfect sphere, if you could take the top and bottom and kind of push your hands together and kind of flatten, not really flatten it, but kind of push that sphere together, that's what Earth kind of looks like. That's kind of the circumference. Okay? So, hope you understand that stuff. If you have any questions for me, let me know. But hopefully see you guys soon.